Welcome, dear friend, to Dreamtime Science. Imagine yourself amidst shelves of ancient books, their spines worn soft under the gentle glow of a bedside lamp. The night outside stretches quietly, stars whispering old secrets through the window. Here, in this calm nook, we invite you to drift gently into stories wrapped in tranquility and wonder. If this moment feels right, a quiet tap of the like button or a soft word shared in the comments about where you listen from would mean the world. Let yourself settle now, adjust your pillow just so, breathe in slow, even rhythms. Together we will wander softly through the twilight realms of knowledge, letting curiosity soothe the mind while sleep tiptoes closer. Whenever you are ready, let your journey begin as we turn the page together. Tonight we'll glide very slowly, very gently into the quiet realm of bosons, tiny whispering particles that dance softly through the fabric of the universe. Like elusive threads weaving the gentle tapestry of all things, they invite our wonder from a safe, pillow-soft distance. Let's drift together into this mysterious world where science hums a lullaby of the unseen. If these cosmic lullabies help ease your mind, consider leaving a quiet like or becoming a regular dreamer by subscribing. I'd love to know which corner of Earth you're exploring from. Now take a moment, adjust your blanket, find the perfect hollow in your pillow, let your shoulders melt, breathe in and out. Beneath everything we witness around us, the sky stretching wide above, the plants growing quietly in the soil, and even the quiet rhythm of our own heartbeat, there exists an astonishing world so small that it eludes our everyday senses. This is the realm of particles, the fundamental pieces from which the universe is woven. Exploring this realm is like embarking on a journey where the familiar dissolves into a subtle dance of invisible actors, patiently waiting to reveal the story of how matter and energy arise, and ultimately how the cosmos itself came to be. All matter, the stars we see twinkling in the night, the mountains rooted firmly to the earth, the air we breathe, and the very cells in our bodies, is made up of particles. But what are these particles? This question has been a guiding light for physicists and philosophers for thousands of years. It might surprise you to learn that our understanding of particles has evolved tremendously over time, shifting from ancient notions of indivisible atoms to the dizzyingly complex framework of modern particle physics. If we rewind to classical times, the Greek thinker Democritus introduced the idea of atomos, literally meaning uncuttable or indivisible. He imagined that everything was made from these minute, solid bits that floated in the void, much like grains of sand or pellets. Although this was a profound insight, it remained a philosophical idea without experimental proof for centuries. It wasn't until the 19th and 20th centuries, with the help of advancing technology, that we began to peel back the layers of the atom and discover that it wasn't the end of the story after all. Atoms themselves, the tiny units of an element, are not indivisible. Rather, they are composed of even smaller particles, protons, neutrons, and electrons. The protons and neutrons cluster tightly together in the center, forming a dense nucleus, while the electrons whirl around this nucleus in fuzzy clouds defined not by neat orbits, but by probabilities. This beautiful arrangement creates the multitude of chemical elements, yet these familiar components are themselves built from deeper layers of reality. Let's consider the proton more closely. For a long time it was assumed to be a humble, elementary particle. But when physicists developed powerful accelerators and detectors, they found that protons and neutrons were not fundamental after all. They have internal structures made of quarks. Quarks are among the tiniest known building blocks of nature. They come in 6 flavors: up, down, charm, strange, top, and bottom. Protons and neutrons contain combinations of the up and down types. These quarks are held tightly together by particles called gluons, which act like an invisible, powerful glue, a fundamental force that binds them with tremendous strength. This discovery opened a remarkable window into a previously hidden world. Quarks, gluons, and electrons, which remain elementary and show no smaller parts so far, are known as the fundamental particles. The science of studying these particles and showing how they interact is called particle physics or high-energy physics. In this field, the most accepted framework for understanding nature's ingredients is known as the Standard Model. It classifies all fundamental particles into different groups and describes their interactions with exquisite precision. Within the Standard Model, particles are divided primarily into 2 categories: fermions and bosons. Fermions are the constituents of matter. Everything that makes up stuff is built out of these particles. Each fermion has a unique property known as spin, which you can think of as a kind of intrinsic angular momentum, almost like a tiny top spinning silently in place. Fermions have half-integer spins, such as 1/2, and this spin quality imparts crucial behaviors, including the Pauli exclusion principle, which says no 2 identical fermions can occupy the exact same quantum state simultaneously. This principle explains why matter is stable and doesn't collapse into a dense blob. Without it, our world would be entirely different. Fermions themselves are separated into 2 classes, quarks and leptons. Quarks, as I mentioned, combine to form protons and neutrons. Leptons include particles such as the electron and its heavier cousins, the muon and tau, plus their associated neutrinos. Neutrinos are particularly fascinating. They are extraordinarily light, electrically neutral, and rarely interact with other matter. Trillions of them pass through your body every second without a trace, produced by reactions in the sun and other cosmic processes. Then there are the bosons, particles that carry forces, the messengers facilitating interactions between matter particles. Unlike fermions, bosons have integer spin values such as 0, 1, or 2. This difference allows bosons to cluster in the same state, which is important for how forces manifest. For example, photons are bosons that carry the electromagnetic force. photons are massless and travel at the speed of light, enabling everything from visible light to radio signals. The gluons I mentioned earlier are also bosons. They transmit the strong nuclear force, binding quarks tightly inside protons and neutrons, the invisible threads that hold the very fabric of matter together. The weak nuclear force is another key player. It is responsible for certain types of radioactive decay, and the sun's ability to produce energy by fusing hydrogen into helium deep within its core. The bosons responsible for the weak force are called W and Z bosons, and they are quite massive, which means the weak force acts only at incredibly short ranges inside atomic nuclei. Finally, there is the elusive Higgs boson, predicted by theory in the 1960s and discovered experimentally in 2012. The Higgs boson is related to the Higgs field, a pervasive field filling the universe. Particles acquire mass by interacting with this field. Imagine swimmers trying to move through a pool of water. Some feel more drag and move slower, effectively gaining mass, while others slide through with ease. The discovery of the Higgs boson confirmed this vital piece of the Standard Model's puzzle and deepened our understanding of why particles have the masses they do. Each of these particles and forces helps build the grand architecture that defines the universe's structure, from the smallest constituents bound tightly in the nucleus of an atom to the vast stretches of interstellar space where matter aggregates into stars and galaxies. These particles and forces are the silent architects behind everything we see. The nature of particles is still an open frontier. While the Standard Model has been incredibly successful, it is not a complete theory of everything. It leaves unanswered questions, such as the nature of dark matter and dark energy, mysterious phenomena that make up the majority of the universe's content, but do not emit or absorb light. Scientists suspect that there may be unknown particles or forces lying beyond the Standard Model, patiently waiting to be discovered with future experiments. As we gaze skyward or study the tiniest specks in a laboratory, we are peering into layers of reality where the ordinary dissolves and gives way to profound simplicity repeated in countless forms. Particles may be minuscule, yet the patterns they form are vast and rich, playing out the symphony of cosmic evolution. It's remarkable to reflect on how human curiosity about the smallest constituents led to the creation of immense tools, particle accelerators kilometers long, detectors that glimpse fleeting traces, and theories spanning decades that allow us to uncover these fundamental truths. And with each discovery, the boundary of the unknown shifts, inviting us to explore even deeper. One of the most fascinating aspects of this realm is the dual nature of particles. They can behave like tiny billiard balls, colliding and bouncing off each other, yet simultaneously they act as waves spreading through space. This wave-particle duality is a cornerstone of quantum mechanics and introduces an element of intrinsic uncertainty. Instead of pinpointing exact positions and velocities, we describe particles using clouds of probability, where certainty gives way to possibility. For example, the electron around an atom's nucleus does not orbit in a precise circle but exists in a cloud of probability, a region where it is likely to be found. This idea challenges our classical intuition, but has been repeatedly confirmed by experiments. Such behavior explains chemical bonding, electric currents, and a multitude of phenomena that underlie modern technology, from semiconductors to nuclear energy. The vocabulary of particles extends beyond just their types. It involves understanding properties like charge, mass, spin, and interactions. Charge is a fundamental characteristic that determines how particles respond to electromagnetic forces. Protons carry a positive charge, electrons a negative one, and neutrons are neutral. The attractions and repulsions due to charge shape how atoms form and how matter behaves macroscopically. Mass, as introduced by the Higgs mechanism, measures how much inertia a particle has, governing how it reacts to forces and moves through space. Spin, while harder to visualize, defines fundamental symmetries and interaction rules in quantum physics. These quantum properties combine in elegant ways, producing the kaleidoscopic patterns of matter and energy around us. One might wonder how it is that such a variety of particles and forces come to work in harmony. The answer lies deep in the symmetries and laws of physics, principles that govern conservation of energy, momentum, and charge. Symmetry principles such as gauge symmetries dictate the form and behavior of forces and particles, much like rules for a complex game ensure order and consistency. As we move forward into exploring particles in greater detail, we will also encounter phenomena where particles change identity, transform, and interact in astonishing ways, sometimes revealing glimpses into energies far beyond what we can currently reproduce on Earth, connecting the smallest scales with the vast cosmos. But for now, it is enough to appreciate that at the core of all things are these minute building blocks, particles that under various conditions combine, interact, and transform, sculpting the universe's complexity from the quantum shadows. Every star, planet, living creature, and human thought arises from the subtle interplay of fundamental particles and forces. Our journey into understanding these building blocks only grows richer with every step, as we learn not just what they are, but how their dance shapes time, space, matter, and energy itself. As we proceed, we'll uncover how these particles interact, the forces that bind them, and the remarkable ways nature balances simplicity and complexity. In the next chapters, we will delve into these interactions, explore the forces conveyed by these particles, and investigate the experiments and discoveries that shed light on their mysterious behavior. This exploration is not just about tiny specks, but about the profound unity underlying the universe's tapestry. So, as we settle more deeply into this fascinating realm, keep in mind that the minute and the immense are woven together by these particles. Their story is a quiet yet powerful one, inviting us to ponder both how the universe is structured and why it behaves as it does. We are at the threshold where curiosity meets the invisible, where the universe whispers its most elemental secrets, and gradually, with gentle steps, we begin to understand the language of reality itself, spoken through the symmetry and rhythm of particles, the true architects of existence. Building on the foundation of understanding the fundamental particles that make up matter, the fermions, we now turn our attention to another essential family in the subatomic world, the bosons. While fermions, with their half-integer spins and the Pauli exclusion principle, form the very stuff of atoms, bosons perform a quite different and equally vital role. They are the carriers of forces, the invisible messengers that govern how particles interact and hold the universe together. To appreciate the grand design of nature, it is crucial to zoom in on these peculiar particles, to understand their unique characteristics and why their existence is central to modern particle physics. Bosons stand in contrast to fermions primarily because of their intrinsic property called spin. Spin is a quantum property that, though it might be likened somewhat imprecisely to a spinning object in everyday life, actually refers to an innate form of angular momentum each particle possesses. But this spin isn't just a number, it dictates how particles behave collectively. Fermions have half-integer spins, like 1/2, 3, 2, and so on, and they obey the Pauli exclusion principle, which means no two fermions can occupy the exact same quantum state simultaneously. This principle underpins the stability and structure of ordinary matter, like atoms and molecules. Bosons, on the other hand, carry integer spins, 0, 1, 2, and so forth, and they don't obey this exclusion rule. This subtle difference has profound consequences. Multiple bosons can pile up in the same quantum state, almost like dancers on an infinitely spacious ballroom floor, overlapping and moving in harmony. This ability to share states gives rise to phenomena that fermions can never display, such as superconductivity and the behavior of lasers. Now, let's look carefully at some of the main bosons and explore what roles they play and which forces they govern. One of the most familiar bosons in everyday life is the photon. The photon is the quantum particle of light carrying electromagnetic force. It has a spin of 1 and a unique property. It has no mass. Photons are responsible for everything from the warmth of sunlight on your skin to the complex interplay of electrons and nuclei within atoms that gives rise to chemistry. Because photons are massless, they always travel at the speed of light in a vacuum, serving as the relentless messengers of electromagnetic interactions. But the photon is just one example. The family of bosons extends to include particles that mediate other fundamental forces too. The strong nuclear force, which binds protons and neutrons inside atomic nuclei, is mediated by a set of bosons called gluons. Gluons are also spin-1 particles, but unlike photons, they carry what is known as color charge, a property unrelated to visual color, but crucial in the theory known as quantum chromodynamics, QCD. The word color here is a convenient label physicists use to describe how quarks, the constituents of protons and neutrons, interact strongly with each other. Gluons glue quarks together, constantly exchanging color charges in an invisible but tremendously powerful dance that holds the heart of matter intact. Unlike photons, gluons themselves carry color charge, which means they can interact not just with quarks, but with other gluons as well. This self-interaction leads to the fascinating and complex behavior of the strong force, such as the phenomenon called confinement. Quarks and gluons are forever trapped inside composite particles like protons and neutrons and cannot be isolated individually. In essence, gluons construct the very core of atomic nuclei, and through that almost all the mass you see around you. Then there are the W and Z bosons, which carry the weak nuclear force. This force is responsible for processes like radioactive decay, where a neutron transforms into a proton, emitting particles in the process. Unlike photons and gluons, W and Z bosons are massive, significantly heavier than even protons, meaning the weak force operates over extremely short distances, about 1/100th the diameter of a proton. These bosons have spin 1 as well, and their heavy mass is why weak interactions are so short-ranged and rare amidst other forces. The story of W and Z bosons is particularly remarkable because their discovery in the early 1980s validated the unification of electromagnetism and weak nuclear force into what physicists call the electro-weak interaction. This was a theoretical prophecy confirmed by careful experiments, earning recognition in the form of Nobel Prizes and deepening our understanding of how seemingly different forces arise from a more fundamental unity. Another boson, not quite as familiar but just as important, is the Higgs boson. This particle made headlines worldwide when it was discovered in 2012 at the Large Hadron Collider near Geneva. The Higgs boson is a spin-zero particle, meaning it has zero intrinsic angular momentum, a trait that sets it apart from the others we've mentioned so far. Its significance lies in the mechanism it reveals. The Higgs field permeates all space, and particles gain mass through their interaction with this field. You might picture the Higgs field like a kind of cosmic molasses or invisible medium that imparts inertia to particles as they move through it. Without this mass-granting phenomenon, fundamental particles like the W and Z bosons would remain massless, and the universe would be a profoundly different place, entirely without the complex structures we observe. This field's discovery represents one of the great triumphs of modern physics, confirming a cornerstone of the Standard Model, our best, though still incomplete, theory of particle physics. There's also a more speculative boson theorized at the frontiers of physics, called the graviton. Unlike photons and gluons, the graviton would have a spin of 2, according to certain quantum theories of gravity that aim to reconcile gravity with quantum mechanics. Gravity, as described classically by Einstein's general relativity, is curvature in space-time, but in quantum theories we imagine gravitons as particles carrying gravitational force. Detecting gravitons has proven elusive so far, largely because gravity is so weak compared to other forces, and we have not yet built instruments sensitive enough to capture their quantum effects directly. What unites all these bosons, photons, gluons, W and Z bosons, the Higgs boson, and perhaps gravitons, is their role as force carriers. They follow a remarkable set of rules described mathematically by gauge theories which form the backbone of the Standard Model. Gauge symmetry, a deep mathematical symmetry underlying these theories, demands the existence of bosons to preserve the consistency and harmony of interactions. Through these particles, the universe communicates. Electromagnetic forces allow atoms to hold electrons in delicate orbits, enabling chemistry and the complexities of life. The strong force binds quarks tightly together to form protons and neutrons, giving rise to mass and stability. The weak force balances nuclear reactions that fuel stars and generate elements essential to biology. The Higgs mechanism explains mass itself, and gravity, the force that governs the grandest cosmic structures, is explored through conjectured bosons, like gravitons. Another intriguing characteristic of bosons, which emerges from their integer spin, is that they obey what physicists call Bose-Einstein statistics. To unpack this simply, classical particles, or fermions in quantum terms, need their own private states, but bosons are more sociable, able to share states without restriction. This leads to fascinating phenomena such as Bose-Einstein condensates, BECs, observed at extremely low temperatures. In a beck, a collection of bosons cools to temperatures just above absolute zero, so cold that they occupy the same lowest energy quantum state and effectively behave as a single quantum entity. This macroscopic quantum state exhibits exotic properties like superfluidity, where fluids flow without viscosity, seemingly defying everyday intuition. What makes Bose-Einstein condensates so extraordinary is that they offer us a window into quantum behavior on scales visible to the naked eye, a bridge between the microcosmic and macrocosmic worlds. The ability of bosons to occupy the same quantum state also explains the operation of lasers. A laser beam consists of photons, all in the same phase and quantum state, resulting in coherent light. It's this uniformity that makes lasers so powerful and precise, used today in countless devices, from barcode scanners to surgical instruments. So far we've talked mainly about fundamental bosons, the ones considered elementary particles, not made of anything smaller. But nature also gifts us composite bosons, particles built from an even number of fermions. For example, mesons are made from a quark and an antiquark and have an integer spin, making them bosons. Even helium-4 atoms contain an even number of neutrons and protons, and they behave approximately as bosons under the right conditions, which is why superfluid helium can form a Bose-Einstein condensate-like state. This composite boson behavior reinforces the universality of the principles governing quantum particles, whether fundamental or composite. To step back for a moment and breathe in the scope of this picture, bosons are the cosmic couriers of force and interaction. Without them, particles would exist in isolation, not interacting, not coalescing into structures ranging from atoms to galaxies. The universe would be a still, silent place without the spark of complexity and change. Their properties, integer spin, obedience to Bose-Einstein statistics, and their role as force carriers make bosons indispensable in explaining how the universe evolves and operates at the most foundational level. This brings us naturally to wonder about the mathematical frameworks that encapsulate bosons and their behavior, the symmetries and principles that describe how these particles arise and interact in quantum field theories. Understanding these frameworks not only illuminates the role of bosons, but hints at the deep underlying order within nature's apparent chaos. We will explore these ideas more closely next, as they reveal how bosons connect the tiniest scales of particles with the grand landscape of forces and symmetries that govern reality itself. Building on the intricate dance of particles and forces we've explored in the last chapter, we now arrive at one of the most profound revelations in modern physics, the Higgs boson, often sensationally called the God particle. This nickname, while a bit dramatic, hints at its fundamental importance in unraveling the mysterious origin of mass itself, a property so fundamental that without it, the universe as we know it would simply not exist. To understand why the Higgs boson captured the curiosity and imagination of physicists worldwide, we need to trace back to the puzzle that lingered for decades. Why do particles have mass? After all, the universe is filled with a variety of elementary particles, the building blocks of matter. But why do some weigh something, and others seem to carry none at all? Photons, the particles of light, have no mass and dart effortlessly across the cosmos at the speed of light. But other particles, like electrons and quarks, the constituents of atoms, possess mass, which makes them slow down, bind together, and eventually form the complex structures we call matter. In the mid-20th century, physicists realized this simple question was, in fact, extraordinarily deep. The mathematics of our most successful theories, known as the Standard Model of Particle Physics, initially treated particles as massless. This was a problem because mass seemed to be a fixed property in reality, so the theory needed a mechanism to turn on mass without breaking its own elegant symmetries and rules. The solution came from an idea first proposed in the 1960s by physicist Peter Higgs, among others. He envisioned an invisible field pervading all of space, now known as the Higgs field. Picture the Higgs field as a sort of cosmic molasses spread evenly throughout the universe. Just as an object moving through honey slows down because of resistance, particles traveling through the Higgs field acquire mass by interacting with it. The stronger their interaction, the heavier they become. Without this field, all particles would be massless, zooming around at light speed, unable to clump together to form atoms, planets, stars, and ultimately living creatures. This explanation profoundly changed our understanding of the universe. It went beyond simply observing particles with mass and revealed why mass exists in the first place. The Higgs field, unlike the electromagnetic field that produces light or the gravitational field that pulls us down, is unique because it imbues particles with mass, a property without which the universe would be a very different, perhaps unrecognizable place. However, theorizing the Higgs field was only part of the journey. If the field exists everywhere, it should be associated with a particle, much like how electromagnetic fields are linked to photons. This particle is the Higgs boson, a ripple or excitation in the Higgs field. Detecting the Higgs boson would be direct evidence that the Higgs field is real. Why did the Higgs boson take so long to detect? The reason lies in the extreme conditions required to produce it. The Higgs boson is exceptionally heavy and unstable, decaying almost instantaneously into lighter particles. To observe it, scientists had to recreate conditions similar to those just moments after the Big Bang. Temperatures and energies so immense that they can only be achieved in the world's most powerful particle accelerators. Enter the Large Hadron Collider, or LHC, beneath the surface of the French-Swiss border near Geneva. The LHC is a ring-shaped tunnel nearly 27 kilometers in circumference, where protons race around at nearly the speed of light, smashing into each other with unimaginable energy. When two protons collide at such velocities, their kinetic energy can briefly create a diverse zoo of particles, including, potentially, the elusive Higgs boson. The experiments conducted there, ATLAS and CMS, are feats of human ingenuity, employing detectors the size of cathedrals, designed to capture the debris of these microscopic collisions. These detectors measure the energy, momentum, and trajectories of countless particles produced in a blink, allowing physicists to sift through mountains of data for the telltale signals of the Higgs. On July 4, 2012, after decades of anticipation, the world learned that the LHC had indeed spotted a new particle consistent with the predicted Higgs boson. This discovery was a watershed moment in science, confirming the final missing piece of the Standard Model. But why exactly was this particle so important? And why did it earn such an emphatic nickname as the God particle? The moniker originated more as a popular media name than a scientific one. Nobel laureate Leon Lederman notoriously called it that in his book, sometimes claiming it was originally the goddamn particle because of its elusiveness, which was shortened for mass appeal. While the label can be misleading, implying that the Higgs holds cosmic or theological significance, the particle's importance cannot be overstated. It's central because it provides the mechanism by which elementary particles gain mass, making it a cornerstone of the Standard Model's completeness. Think of the universe before the Higgs field switched on. In those earliest moments after the Big Bang, when temperatures were unimaginably high, the Higgs field was essentially off. Particles were massless, zipping around at the speed of light, unable to bind or form structures. As the universe cooled, the Higgs field transitioned to a non-zero value, suddenly giving mass to fundamental particles and allowing matter to coalesce, stars to ignite, and galaxies to take shape. Delving deeper into the properties of the Higgs boson reveals fascinating characteristics. It is a scalar particle, which means it has no spin, a property describing intrinsic angular momentum that particles like electrons have. The Higgs is unique in this regard, making it especially challenging to detect since it doesn't produce the same patterns or signals other particles might. Moreover, the mass of the Higgs boson itself, measured around 125 giga-electron-volts, is somewhat puzzling. This number is not predicted by current theory, but must be measured experimentally. Its specific value has major implications for the stability of our universe. Some theoretical work suggests that at higher energies the Higgs field could become unstable, potentially triggering a dramatic transformation of the vacuum state of the universe, a concept both intriguing and unsettling, though such events would be unimaginable on human timescales. The discovery of the Higgs boson also opens doors to new mysteries. It doesn't answer all questions, nor does it explain everything about mass. For example, most of the mass of protons and neutrons comes not from the Higgs mechanism, but from the strong force that holds quarks together. The Higgs field imparts mass to the quarks themselves, but the energy from their interactions, the strong nuclear force, provides most of the observable mass in ordinary matter. Furthermore, the Higgs boson hints at physics beyond the Standard Model. The Standard Model is extraordinarily successful, yet it leaves certain profound questions unaddressed. What is dark matter? Why does the universe have more matter than antimatter? Models extending the Higgs mechanism, considering multiple Higgs bosons or interactions with other unseen fields, are active areas of research. Each insight gained from the Higgs helps steer us closer to a deeper, more unified understanding. Observing the Higgs boson was not just about confirming a particle's existence. It was affirming a concept that reshapes our cosmic narrative, connecting the smallest scales of quantum mechanics with the grand tapestry of the universe. It is a subtle reminder that fundamental forces and fields, invisible to our eyes, govern everything from the light emitted by stars to the very matter composing our bodies. Consider this: if the Higgs field did not interact with electrons, atoms would have no size. Electrons would simply pass through the space around an atomic nucleus at the speed of light, unable to form stable orbits, and matter could not exist as we know it. we would be left in a universe filled only with radiation, a cold and featureless expanse. In a poetic way, the Higgs boson reveals the delicate balance underlying the physical world. The universe's fabric is woven by these fields and particles, invisible in the daylight of daily life, yet fundamental to all reality. Through vast international collaborations, cutting-edge technology, and years of theoretical and experimental effort, humankind has peeled back this veil, revealing a gem that guides us through the complexity of existence. As the LHC continues its work and future colliders are planned, the Higgs boson remains a beacon for discovery. It might turn out to be a signpost pointing toward new physics realms, perhaps connected to dark energy or the unification of forces. Each experimental refinement might reveal subtle anomalies or confirm delicate theoretical predictions. Remember, the Higgs field isn't some exotic addition, but the silent backdrop to all particle interactions. It reminds us how the universe, in all its vastness and complexity, relies on the interplay of the unseen and mysterious to give rise to matter and life. From a field that permeates every corner of space, we gain the structure to ask questions, to learn, and to dream. This brings us naturally to the next step in our exploration, how the Higgs fits into the grander quest for a unified theory of everything. If the Higgs field is one thread, then the forces of nature and their corresponding particles weave others, sometimes pulling in directions we don't yet fully understand. The story of the God particle opens a gateway to these larger mysteries, inviting us to peer deeper into the cosmic code still waiting to be deciphered. Building on the profound revelations about bosons and the Higgs field, it's worth pausing to reflect on how this deepened understanding has rippled through modern science, reshaping our view of the universe and guiding new avenues of discovery. The story of bosons is not merely one of particles or equations tucked away in laboratories. Rather, it illustrates a fundamental shift in how we perceive nature itself, blurring the lines between the abstract and the tangible, the theoretical and the experimental. This reflection is an invitation to appreciate the wide-ranging implications the Higgs boson and its counterparts hold for physics and beyond. At the heart of this reflection lies a recognition that the discovery of the Higgs boson, often dubbed the God particle, marked a monumental milestone in experimental physics. It was the final piece of the Standard Model, the elegant mathematical framework describing three of the four fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, as well as the fundamental particles of matter. Before the Higgs boson's discovery in 2012 at CERN's Large Hadron Collider, the Standard Model was incomplete, much like a beautifully antiquated clock missing its pendulum. Without this particle, the explanation for why many particles possess mass was absent, leaving a critical question unanswered. How do particles acquire mass at all? Unveiling the Higgs boson did more than simply confirm a decades-old prediction. It validated the existence of the Higgs field, an invisible, pervasive energy field stretching across the entire cosmos. You might be tempted to think of fields as ethereal, lacking substance, but the Higgs field is the very essence from which mass emerges. When certain elementary particles interact with this field, they slow down and resist acceleration, which manifests as the property we call mass. It's a subtle dance of nature. Particles like photons, which do not interact with the Higgs field, remain massless and race at the speed of light, while others like the W and Z bosons acquire significant mass. This elegant mechanism beautifully explains a long-standing puzzle, reconciling symmetrical equations with the asymmetrical reality of our mass-bearing universe. But beyond settling the theoretical void of the Standard Model, the understanding of bosons, particularly the Higgs boson, has opened new realms of inquiry that stretch deep into the fabric of reality. The pursuit to detect the Higgs boson required massive experimental innovation and technological advancement, culminating in the construction of colossal and highly precise instruments like the Large Hadron Collider, LHC. This scientific behemoth pushes particles to energies comparable to those just fractions of a second after the Big Bang, enabling us to peek at the newborn universe and test the very laws that govern existence. This journey is a testament to human curiosity and ingenuity, illustrating how fundamental particles, once only theoreticians' musings, anchor the vast infrastructure of high-energy physics experiments. The technologies developed for particle accelerators and detectors have cascaded beyond pure research, influencing fields such as medical imaging, cybersecurity, and materials science. For example, the World Wide Web itself famously originated at CERN, a byproduct of the global collaboration intrinsic to such endeavors. Thus, the study of bosons is entwined not only with the deepest questions of nature, but also with pragmatic advancements that filter into everyday life. The discovery of the Higgs boson also reinforced the notion that the universe operates according to principles that are both elegant and surprisingly accessible to human investigation. It highlighted the extraordinary predictive power of quantum field theory, the language through which physicists describe particles as excited states of underlying fields. The Higgs boson is itself a quantum excitation of the Higgs field, reminding us that particles and fields are part of a unified conceptual framework. Understanding one enriches comprehension of the other. This duality expanded our grasp of symmetry breaking, a concept that explains how uniform conditions in the early universe evolved into the richly structured cosmos we inhabit, where forces and particles differentiate themselves with distinct properties. Symmetry breaking, as revealed by the Higgs mechanism, is not a niche idea confined to particle physics, but resonates throughout many branches of physics and beyond, it catalyzes the formation of complex structures from crystals to galaxies. This insight has inspired researchers in condensed matter physics, cosmology, and even string theory, where analogous mechanisms govern phase transitions and the emergence of new physical realities. Thus, the knowledge of bosons acting through fields has transcended its initial domain, serving as a bridge connecting disparate scientific disciplines. On a more philosophical level, understanding bosons and the Higgs boson invites us to reconsider what we understand by existence and reality. The Higgs field, though invisible and intangible, is as real as the particles it endows with mass. This defies everyday intuition, shaped by direct sensory experience, guiding us to appreciate that the universe's true nature unfolds in layers beneath surface appearances. It encourages a form of scientific humility and awe, acknowledging that reality is richer and more intricate than immediately visible. Another profound implication is how the discovery has energized the search for physics beyond the standard model. While the Higgs boson completes the standard model's particle family, puzzling questions remain unanswered. For instance, the standard model does not include gravity as described by general relativity, nor does it explain dark matter or dark energy, mysterious components that account for nearly 95% of the universe's total mass-energy content. Furthermore, the Higgs boson's measured properties, especially its mass, open theoretical debates about the stability of our universe's vacuum state, nudging physicists toward concepts of multiverses or alternative cosmic histories. Studying bosons in intense detail now helps physicists look for subtle deviations in Higgs boson behavior that might hint at new physics. Could there be undiscovered particles that interact with the Higgs field? Might the Higgs boson itself be part of a larger family awaiting discovery? Answers to these questions might unravel pathways toward a grand unified theory, one that weaves together all fundamental forces. The LHC and future powerful colliders, like the proposed Future Circular Collider, are constructed with these mysteries in mind, underscoring how the Higgs boson's discovery invigorated efforts pushing the frontiers of particle physics. Moreover, bosons hold a pivotal role in emerging quantum technologies, an area promising transformative impact on computing, communication, and sensing. Photons, the quintessential bosons responsible for electromagnetism and light, are harnessed in quantum information science to realize quantum bits or qubits that outperform classical counterparts. By mastering the quantum states of bosonic particles, scientists hope to unlock unprecedented computational power, cryptographic security, and new modes of measurement. Thus, the fundamental understanding of bosons becomes a stepping stone along the path from abstract theory to revolutionary technology. Even within astrophysics and cosmology, bosons continue to be central characters. Neutrinos, although technically fermions because of their half-integer spin, interact through the exchange of bosons, like the W and Z bosons, playing critical roles in supernovae explosions and the synthesis of heavy elements. More intriguing still is the hypothetical existence of bosonic dark matter candidates, such as axions and dark photons, which, if detected, would lift the veil on one of the universe's greatest mysteries. The ripples of understanding the Higgs boson extend further into how science operates as a global enterprise. The discovery epitomizes collaboration, transcending borders and cultures, uniting thousands of researchers in pursuit of a common goal. It underscores the importance of patience and persistence in scientific inquiry, reflecting decades of meticulous theoretical work followed by equally meticulous experimentation. This human story of bosons is one of collective endeavor, reminding us that the pursuit of knowledge is a shared journey fueled by wonder. As this exploration winds toward a close, it is valuable to appreciate that the story of bosons, and especially the Higgs boson, is far from finished. Each experimental run, each new theoretical insight, nudges open doors to deeper understanding and new questions. Science thrives on such continual unfolding, much like a quiet river carving the landscape slowly yet ceaselessly. In coming chapters, we might consider how these foundational insights might influence future physics paradigms, perhaps hinting at the enigmatic realm of quantum gravity or at the unification of all forces in a yet undreamed theory. The Higgs boson, once elusive and theoretical, now acts as a keystone in bridging known and unknown, a remarkable testament to human curiosity unlocking nature's secrets. So tonight, as you drift into rest, remember that beneath the comforting stillness of this moment lies a universe governed by invisible fields and particles, dancing to the quiet tune of fundamental forces. The bosons, bridging the unseen and the tangible, whisper stories that stretch from the infinitesimally small to the vast expanse of the cosmos. Their tale is far from over, and in this continuing narrative, every question answered is a gateway to new wonder, a gentle invitation to keep exploring, dreaming, and discovering. As our journey through the shimmering realm of bosons gently drifts to a close, we watch their elusive dance fade like a comet tail into the hush of space. May the quiet wonder of these tiny messengers cradle your thoughts tonight, inviting peaceful dreams of the universe's secrets yet to be told. Return soon, dear dreamer, for more starry tales to softly unfold beneath the velvet sky.